Hello students, let us begin Module 11. Module 11 is a continuation of Module 10, as you can see from the title. It's coming from the same chapter, Chapter 6 of our textbook. So let's begin with a review on Module 10 materials, and here we go. This is how we define the scalar product. A scalar product is a binary operation from an abstract vector space V to the set of real numbers R. And the scalar product must satisfy these four properties, and the first is it must be symmetric. V.W is the same as W.V, or the first vector times the second vector is the same as the second vector times the first vector. Symmetric, or commutative. Next, bilinear. We can separate the addition, like this, and we can separate the scalar multiplication, like this. Now this and that are for the vector v, the first vector, and this and that are for the second vector, vector w. However, what's the difference between v and w? Well, there's none. They're the same because of the symmetry. So whether we write the second part like this and that or not doesn't really matter. Our textbook author decided not to write this part and that part. But me, on the other hand, my philosophy is usually to include everything unless there are some reason for confusion, even if there are some redundancies. So I decided to include everything here. Okay, let's move on to the last property here. Positive definite. For any vector, the scalar product by itself is always non-negative and equal to 0 if and only if it is a zero vector. Here's an equivalent expression of the scalar product. It's a binary operation, of course, and symmetric, positive definite, but in terms of bilinearity, we can use the linear combination instead of addition and scalar multiplication separately. This is for the first vector, and that's for the second vector. Either way, you can define scalar product. It doesn't matter which way you do, they're equivalent. Now, norm. Norm is a square root of the scalar product of itself, or equivalently speaking, norm squared is the dot product. So whenever you do some algebra with norms, typically we consider norm squared because square root is really difficult to deal with. These are the properties, and it's easy to show. You can use the property of square root and get this C out. The detail is left to the students. And this one, positive definite, that's not even worth discussing. It's really trivial. The middle one, on the other hand, this is a tough one, subadditivity. If we have nice geometrical structure, you can prove it like this. Begin with norm square and then take the scalar product of itself, fold it out, and then first and last, those are norm squared, those are okay, but the middle term, V.W, that's the scalar product, and you can overestimate this part by the product of the norms, and that's because V.W is the same as norm of V times norm of W times the cosine of theta here, where the angle theta is the angle between those two vectors. And cosine of theta, of course, is always less than or equal to 1, so we have this inequality and everything works fine. The problem is, if we do not have nice picture, if you don't have the angle, in that case this does not work out very well. And can we still do this? The answer is yes. The norm is always less than or equal to, the inner product, the scalar product, is always less than or equal to the product of norms, and that's called Cauchy-Schwarz inequality. And using Cauchy-Schwarz inequality, you can prove this in abstract vector space. in abstract vector space with abstract norms and scalar product, it'll still make sense. An example like this one, you see. Let's see. Yes, the typical example, this is same as geometry, so there's no problem there. And already this is going to be a little bit tough. We have some matrix here, and as long as this matrix is symmetric and positive definite matrix, it's okay. But already geometrical structure is kind of skewed already. But what if we do something like this? Now we are completely out of any kind of geometry. What is the angle between these two functions f and g? They don't make any kind of sense at all. Yet you can still conclude the subadditivity and all those kind of things. That's because of Cauchy-Schwarz inequality. Okay, let's move on. Unit vectors, oh, that's trivial. We are talking about a vector in the direction of v, so it should be a scalar multiplication, some scalar times v, so it points to the same direction. And as for the magnitude of this, simply take the norm and do some simplification. You'll see that norm is 1. Next, orthogonality. We say a pair of vectors v and w are orthogonal if the scalar product is 0. Okay, so if you use this cosine of theta concept, you'll see cosine of theta is 0 when we have right angle, so this corresponds to the right angle. However, if you use the definition using the orthogonality, the scalar product, then you can use the orthogonality for the kind of space that has nothing to do with the angles or any kind of geometry. You can still apply Pythagorean theorems and things like those for abstract vector space. And this is something we are going to do. But before moving on, let me make a point here. This is the Pythagorean law. Left-hand side is hypotenuse squared. So hypotenuse squared is equal to one side squared plus the other side squared. Now, if we have a right triangle, yeah, this is perpendicular, so right triangle, then we know this is true if we have all those pictures and geometrical structure. Great, but then again, how do you prove it? Well, I'll leave that detail to the students. If you go to internet search and then look up the proofs of Pythagorean theorem in Euclidean geometry, then you'll see a lot of different types of proofs. And this is a 3000 level course, so students will not have too much trouble going through all those proofs, but still, they can be complicated. They can be difficult to understand. But if you use abstract algebraic concept using scalar product, it becomes just a one-liner. So sometimes the abstraction and making things difficult to understand in early stage is very, very beneficial in other parts, just like this. So the earlier part, the abstraction may be a bit of an obstacle, but because of that, a lot of technical part became really easy now. This is just one example. Okay, let's go over to the next topic here, parallel and orthogonal component vectors. And let me show you a visualization here. And here we go. Given vector w, and that should be non-zero vector, so we have to have certain direction. And arbitrary vector v can be decomposed into parallel component vector, p of v in w direction, and orthogonal component vector, o of v in w direction, so that p plus o is equal to v, as you can see in this diagram here. You can clearly see that from this rectangle. Now, this parallel component vector is in w direction, so it must be written as a scalar multiplication of something times w. There's no question about that. Something times w. But what is that something? What is that c? Turns out that c is equal to v dot w over w dot w. Please remember this formula. The deviation you may forget, but the formula itself, v dot w over w dot w, you should remember this. And of course, v minus of that is perpendicular, orthogonal, as you can see here. And of course, if I add up this expression and that expression, they cancel out and we get v. You can clearly see that too. Okay, this is for just one vector, w. V and then just one vector w, so that we can find out the parallel component vector and orthogonal component vector, green and brown like this. Now what if we have more than one such direction vectors, w1, w2, w3, w4, and so on and so forth? It's this one. So we get w1, w2, w3, w4 all the way over to wn, and they are mutually perpendicular non-zero vectors. Then we're going to get c1, w1 plus c2, w2 plus c3, w3 all the way over to cn, wn added up together. And this vector is called the orthogonal projection. And it'll turn out this orthogonal projection, which is highlighted in red, is the best approximation of original vector v in this subspace generated by w1, w2, w3 all the way over to wn. And this v minus this orthogonal projection, that is the orthogonal component vector that is perpendicular to everything in that vector space, in the subspace generated by w1, w2 all the way over to wn. Here's a visualization, and first, this is not very good picture by some rotten luck. Okay, still too close. Let me run it again. This program is randomized. Okay, alright, I like this picture. I mean, sufficiently large so that I can actually see how things are going. Alright, so let's look at the first picture. Let's consider a light source, a flashlight on top, and then project light straight down orthogonally. Then the shadow of this blue vector is this red, c1, w1, this red vector. So this is the orthogonal projection given by that light source. And v minus that c1, w1 is this perpendicular, this vertical, and that's the orthogonal component vector. So we're talking about just c1, so I don't have any of those. So v minus c1, w1, that's this vertical. Now, if you go to the right-hand side, this A1, A2, A3, these are arbitrary. So if I run this program again, I'm going to get still different triangle here because this selection is arbitrary. Now, what's the difference? Difference between the tip of this blue and this tip of red is straight vertical, and that's as small as possible. Now, distance between this tip of blue and tip of green, which is randomized, this is slanted, so it's bigger. In other words, this red vector is the best approximation of this vector v within this one-dimensional subspace down here. If I select something arbitrary, like A1, W1 here, the error is the length of this green line is slanted, so it's bigger. So this is better approximation than that. So this one is better approximation than this guy. So the orthogonal projection is the best approximation, and v minus this orthogonal projection is the orthogonal component vector. It's perpendicularly going up. This program is randomized, so I can run it again, and I get still different picture, still different slanted. Still, this green is longer than this straight red. You can clearly see that. Now, what if I go over to one higher dimension is kind of like this. This is blue vector, and then we take the light source straight up and then project down, and you can see that this red vector down there is a shadow of the blue vector. So this red vector, which used to be down here, which is kind of blocked right now, that's the orthogonal projection. Now let's change the viewpoint. Okay, does it really, does it really look like orthogonal projection? Straight down, yes indeed. And then this vertical distance is the smallest possible distance. It's this point. Now, this selection is arbitrary, so we have this green vector here, and then distance, that's slanted distance. So that should be longer. How do I see this thing a little bit better? Okay, maybe it's better this way, about this. Okay, all right, here. This is straight, and this one is slanted, so green is longer. So this is better approximation, this is better approximation of V, so the difference is the shortest, smallest possible error. And then how do you get that orthogonal projection? Each of these C1, C2, C3, those are these components that we discussed earlier. Same formula here. V dot W over W dot W. Here, V dot Wi over Wi dot Wi, because there are many of those here. The proof, well, we already discussed the proof in the previous video, so I'm going to go really quickly. So you can skip this playback if you're not interested in the proof, because we already did it. But in any case, let's go from here. Let's take Wi dot V minus this orthogonal projection, and then do some algebra. Break up all those brackets, and then what do you get? V dot Wi, all right. And then W1 dot Wi. Next will be W2 dot Wi. And then W3 dot Wi all the way over to Wn dot Wi. All these dot products are going to be 0 because all these W's are mutually perpendicular. So all those red things, W1 dot Wi, W2 dot Wi, all the way over to Wn dot Wi, they're all zeros, except of course the dot product of itself, Wi dot Wi. Now drop all these 0, and for this one, what is Ci? Ci is this, V dot Vi over Wi dot Wi, and this Wi dot Wi in denominator, and this Wi dot Wi cancel each other out, and after some algebra, what do you get? We get 0. So they're perpendicular. Because this one is perpendicular, we can just elongate a little bit in the same direction. What do you get? This scalar times this dot product is scalar times 0, so we have 0. Does it help? Oh yes, indeed, because this dot product that is 0, and the second term dot product of that is 0, and also the last term dot product of that is 0. So basically we are just adding a bunch of zeros, so that's 0. Consequently, this expression and the V minus orthogonal projection, the orthogonal component vector, are perpendicular, and consequently we can apply the Pythagorean identity. The arbitrary distance V minus green can be written as V minus red plus red minus green, and then this part can be rewritten as before by taking appropriate vectors, and as you saw before, this and that are perpendicular, so we have Pythagorean rule. We have this equality. And finally, dropping this always non-negative value, we're going to be decreasing a little bit. So we got the inequality. That is the sketch of the proof.